Dark matter is a lie, NASA's cover-up for broken gravity. The rotation curve on the screen stayed flat when it should have plunged. A young postdoc froze, coffee cup slipping from her hand and shattering on the floor. If that line was right, gravity, our most trusted law, had failed on the scale of galaxies. Observatories kept stacking data. The line stayed flat. Here's the claim: gravity is broken and dark matter is the bandage. Agencies knew something was off from the first galaxy rotation curves in the 198s. But here's the thing: the fix got political fast. We're naming names, posting dates, and following people who had to choose the story or the truth. Stay with me. When gravity first failed, the rotation curve Revolt. If Newton's gravity worked the way we teach it, stars far from a galaxy's center should slow down. Less mass inside their orbit means weaker pull, so orbital speeds should fall with distance. Instead, when Vera, Rubin, and Kent Ford pointed spectrographs at Andromeda's outskirts, the speeds refused to drop. The curve was flat. Then galaxy after galaxy did the same thing. Stakes right up front. If galaxies shouldn't hold together under known gravity, then our map of the universe is built on sand. Structure formation, cosmic web growth, even how we weigh the cosmos, everything assumes gravity tells the truth. If it lies at low accelerations, cosmology cracks. Rubin didn't go hunting for a revolution. She was careful, methodical, obsessed with getting the data right. In the 198s with Kent Ford and Norbert Thonard, she published rotation curves for spirals across a huge range of sizes and luminosities. The outer parts didn't taper, they stayed fast. It wasn't a one-galaxy fluke or a sloppy instrument bias. The pattern was stubborn, repeatable, and loud. Meanwhile, theorists faced a fork. Either gravity changes character in those faint outskirts where accelerations are tiny, or there's more mass than we can see. The community branded the second option, missing mass soon, dark matter. The story hardened quickly. Each galaxy sits inside a vast halo of invisible, collisionless stuff. That halo boosts the pull and keeps stars whipping around at high speed without shredding the disk. Action exploded. Simulations wrapped luminous disks in spherical halos and recovered flat rotation curves. Radio telescopes traced neutral hydrogen far beyond the starlight, and the velocities still stayed up. Infrared maps anchored stellar mass where dust hid it. X-ray telescopes weighed hot gas in clusters and found even more mass missing. Everywhere the curve should fall, it didn't. The standard model, general relativity plus ordinary matter, survived by outsourcing the anomaly to an invisible fix. Here's where choice entered the room. Rubin kept her language cautious. She didn't claim a new substance, she reported what the sky insisted on. There is something we don't understand. But within a few years, Halo slid into textbooks as if it were a property of nature, not a patch. Students learned to decompose rotation curves into bulged disk, gas, and a dark halo with adjustable parameters. If a galaxy didn't fit, tweak the halo. Why care? Because choosing a patch changes what gets funded, published, and believed. Dark matter seemed to fix more than rotation curves, clusters, gravitational lensing, and later the cosmic microwave background. The more problems it touched, the faster momentum snowballed. If gravity itself was wrong, it threatened decades of work. Careers, instruments, even the vocabulary, mastolite, concentration, locked around the bandage. Meanwhile, something else emerged. Regularities too crisp to look accidental. Ghostly, low surface brightness galaxies still trace stubbornly flat shapes. The baryonic Tully-Fisher relation, total baryonic mass linked to outer rotation speed, came out frighteningly tight. It hinted that visible matter knew exactly how much extra pull the system would show. Dark matter could fit any galaxy with a tailored halo, sure, but why did those fits need so little freedom once you knew the baryons? Back in seminar rooms, there were two moods. Publicly, cosmologists sold the clean story. Unseen matter holds galaxies together. Privately, some winced at the coincidence that the discrepancy lights up when accelerations drop below a tiny threshold. If the universe runs on simple rules, Why would messy halos align so neatly with luminous matter? Observers pushed hard on systematics. Could gas dynamics, bars, or non-circular motions fake flat curves? Teams mapped two-dimensional velocity fields to catch subtle warps. The answer didn't budge. Even after cleaning, curves stayed flat. The Revolt wasn't going anywhere. Impact arrived fast. With halos in place, lambdictum, cold dark matter plus a cosmological constant, took shape. It explained large-scale structures' clumpy pattern and promised to match the microwave background's acoustic peaks. Rotation curves looked like the first domino justifying an invisible sector. Press releases simplified. The universe is mostly dark matter and dark energy. The qualifier, if gravity is right, got trimmed. Here's the psychological trap. Once a story reads clean, your brain stops looking for splinters. Now the human angle and the first micro-choices that made a lie by momentum. A grad student plotted a flat curve and asked if they should add halo to the figure. It reads better, their advisor said. They did. In a press office, a scientist wrote consistent with dark matter, and a comms officer trimmed it to direct proof for a headline. In a referee room, a clean MOND comparison got cut for space, while a halo fit with 3 parameters slid through because it matched the default. Nobody lied. They chose the nicer story. Meanwhile, a few voices stared at the curves and whispered the unsayable. Maybe gravity changes when accelerations are tiny. Not distances, accelerations. Maybe at the edges of galaxies, Newton needs help. They didn't write memos. They wrote equations. One of them, an unassuming physicist with a threshold number in his head, refused to add invisible halos and penned a rule that shouldn't have worked. It did. The Insurgent equation, MOND's dangerous simplicity. His name was Mordehai Milgrom, quiet voice, stubborn compass. He kept circling one clue everyone else kept stepping over. The mismatch wasn't about distance, it was about acceleration. In 1983, he wrote down a threshold, call it about 1, 2 times 1010 ms2. Above it, Newton and Einstein. Below it, something shifts. Not a new particle, a new regime. Stakes on the table. If one universal scale governs how galaxies rotate, and if you can predict those curves from what you can see, stars and gas, before measuring them, then halos start to look like elegant epicycles. You don't just tweak. You risk collapsing a scaffold that props up careers, simulations, and a public story that's easy to teach. If MOND works in disks, the bandage peels. Milgrom's move was surgical. In the deep MOND limit, the effective acceleration isn't Newton's Gn, it's roughly SQRT, Gn. That's just enough to hold stars in place without hidden mass. 2 hammer blows fall out. First, asymptotically flat rotation curves, velocities stop dropping and level off. Second, the baryonic Tully-Fisher relation, V4 approximately G m baryon. Velocity set by visible mass and one constant. No halo dials, no concentration priors. Action jumped from chalkboards to galaxies. Observers took infrared maps for stars, 21 centimeter radio for gas, and with a fixed drew rotation curves. Not fits with 3 free parameters, predictions. Low surface brightness galaxies, where dark matter should dominate, became the clean shot. MOND traced their flats and their bumps. Dwarf irregulars. The weird wiggles in speed echoed the clumps of gas you could actually see. Micro story. A grad student overlaid the gas map on the speed plot and grinned when a knot at 7 kiloparsecs made the same kink in both. The wiggle S in the galaxy, she said, and the curve knows it. Meanwhile, a new regularity tightened the screws. Plot the observed acceleration at each radius against what baryons alone predict, the radial acceleration relation. The points hugged a curve with tiny scatter, bending right where a lives. MOND had planted that bend in 1983. The sky wrote it in data decades later. Here's the but. Solar system tests sit far above us, so MOND must fade to Newton smoothly. That means you need an interpolation function bridging the regimes. Some choices looked great for spirals and awkward for planetary dynamics. Others passed planetary tests but stumbled on non-circular motions. The theory space narrowed. MOND's defenders said, "Good, that's how you learn." Critics said, "You're picking the function after the fact." The fair answer was a protocol. Freeze the function and take the hits in public. Clusters were the second but. Even with MOND's boost, rich clusters still looked short on mass, especially in their cores. Options appeared: unseen baryons, massive neutrinos, or a deeper fix. And lensing bending light demanded a relativistic backbone. Bekenstein built TVS, a tensor, vector scalar framework that bends light and tweaks dynamics together. It worked in places, grew complicated in others. The simplicity badge picked up a scratch. The human beats got sharp. In a seminar, a senior cosmologist quipped, "Nice curves, shame about the universe." The speaker flipped to a slide with 30 galaxies and 1A. "We posted these before the data arrived," she said. "If we're wrong, it's on the record." Afterward, a postdoc from the audience emailed, "Your DDO 154 outer points, annoyingly accurate." It wasn't a conversion, it was a crack. Meanwhile, lambdictum pushed back with its strengths. "We own the CMB," they said, and they weren't wrong. The acoustic peaks, baryon acoustic oscillations, growth of structure, lambdictum nails those with a compact parameter set. Galaxy formation is messy. Feedback bars and mergers smear clean relations. A theory that embraces that mess predicts populations, not perfect lines. MOND answered with the same line every week. Then why is the scatter so small? Here, S where it gets uncomfortable. A's value rhymes with C times the Hubble parameter, a cosmic rate baked into expansion. That coincidence tempted a deeper story. Maybe low acceleration behavior is tied to spacetime's thermodynamics. Emergent gravity ideas waved from down the hall. Tempting, but the rule today still had to write tomorrow's number on a specific galaxy plot. Microstory. A referee asked an author to remove MOND from a title to avoid distracting controversy. The author cut the word and kept the figure. The figure showed a predicted curve hugging data, one constant fixed months earlier. The paper got accepted. The label changed, the number didn't. Meanwhile, the particle hunt silence gave MOND oxygen. Underground xenon stayed quiet. Colliders found no supersymmetric family for WIMPs to join. Axion scans marched, patient and meticulous. The scoreboard didn't move. If the invisible sector kept receding, a law with one scale looked less like heresy and more like a necessary fail-safe. Not a victory, a lever. Impact on culture, subtle. A few groups adopted pre-registration. Name galaxies, fix the interpolation, lock stellar mass-to-light ratios within tight priors and publish predictions. No moving goalposts. Misses counted against the idea, hits counted for it. The tone shifted from slogans to dates. Then came the wager the establishment thought would bury the insurgent rule. If mass can peel away from normal matter in violent mergers, halos become more than bookkeeping. A single image would turn into a sword and a shield at once. They pointed telescopes 3,800,000,000 light-years away and waited for the shock front to light up. The bullet cluster becomes a sword. 3.8 billion light-years away, two galaxy clusters tore through each other. Gas slammed gas, shocked to tens of millions of degrees, glowing hard in X-rays. Galaxies, mostly empty space, sailed through like beads on threads. Then came the map that would set the tone for a generation. In 2006, the bullet clusters overlay hit screens. Stakes first. If the gravitational mass separates from the hot, glowing gas, the baryons we can see, then the thing that pulls isn't just ordinary matter. One picture and halos turn from a fitting function into a claimed substance. For folks calling halos epicycles, this was a punch to the ribs. Action moved fast. Chandra traced the shock front, a clean Mach cone etched in red-hot plasma. Weak-lensing teams measured how background galaxies got sheared by the cluster's gravity, stacking tiny distortions to reconstruct a mass map. The blues, the inferred mass peaks, didn't sit on the X-ray gas. They hugged the galaxies that had passed through. Read simply, collisionless stuff kept going. Collisional gas lagged behind. Press offices loved the phrase direct proof of dark matter. Headlines printed it like a verdict. Here's the choice, not a coincidence. A PI wrote consistent with collisionless mass into the draft. A comms officer trimmed it to direct proof to land the story. A colloquium speaker rehearsed, MOND is effectively falsified, and cut the slide on lensing systematics to make time. A referee waved through a paper that treated the offset as decisive, while another told a modified gravity rebuttal to include a full cosmological model or be quiet. Nobody forged data. They sealed the narrative. Meanwhile, MOND needed a spine to speak lensing. Bekenstein's TVS stepped up, extra fields braided with Einstein's tensor to bend light where the dynamics said gravity should be. Could a relativistic MOND move lensing potentials away from gas in a merger? On paper, maybe. Nonlinear fields, external influences, and even a soupçon of unseen but ordinary baryons might shift peaks. It wasn't elegant. It kept the door from slamming. Observers did their job, pushed the uncertainties. Lensing reconstructions depend on background source redshift distributions, mass sheet degeneracy, line-of-sight structure, shape-noise calibration. Gas physics is messy: shocks, turbulence, magnetic fields, conduction. Even within lambdictum, the bullet cluster set limits on how much dark matter can self-interact. If it's scattered like gas, the blues wouldn't sit cleanly with galaxies. Cross-sections got squeezed. Microstory: a grad student dragged lensing contours over the X-ray image at 2 a.m. and felt their stomach drop. The offset wasn't subtle. They reran the shape catalog, shuffled noise realizations, and the peak stayed put. The PI told them to write the figure first. In another building, a theorist stared at the same overlay and scribbled TVS deflection, with a circle around external field. Everyone slept less that week. Impact was tidal. The bullet cluster turned into institutional armor. Slideshows opened on the red-blue overlay. Telescope time requests cited it. Textbooks added the figure. The narrative hardened. Galaxies trace dark matter, gas lags. The qualifier, if lensing reconstruction assumptions hold, rarely survive to the first paragraph. For lambdictum, this was a rallying flag. For modified gravity, it looked like a funeral. But there was one problem. A single poster child can't carry a field. When other mergers got mapped, MACS J0025, for 1222 El Gordo, Abell 520, the story got noisy. Some showed clean offsets like the bullet. Others displayed dark cores, near gas peaks, or messy mass distributions that strained the simple tale. Projection effects could sculpt weird maps. Triaxial halos and substructures could fake peaks. The neat rule: mass with galaxies, gas behind, needed footnotes. Meanwhile, something else changed: how proof got defined. Lambdictum folks said, population studies, not anecdotes. MOND folks said, relativistic models predict specific offset patterns, test them by date. A few teams pre-registered lensing pipelines, fixed source redshift priors, fixed smoothing kernels, public code, and posted target clusters ahead of time. Misses would count. Hits would matter. It sounded boring. It was the only way out of slogan wars. Human choices stayed human. A communications officer kept consistent within paragraph 2 after a fight. A department chair moved a modified gravity session from the last afternoon to mid-morning. A grant panel funded one clean lensing test with frozen priors and cut a safer simulation extension. They wrote, high risk, field shaping if null. That's a sentence you can feel. Where does that leave the sword? Sharper than critics wanted, duller than headlines promised. The bullet cluster is strong evidence for a collisionless component in that system under standard gravity. It isn't a universal veto on modified dynamics with a relativistic backbone and auxiliary mass. The honest read forces a different question. If halos are real, where's the particle? If halos are stories we tell to make lensing maps make sense, where's the law that writes those maps from baryons alone, on time, with no knobs turned after unblinding? While clusters taught us how to argue, basements taught us how to wait. The detectors got colder, the rooms got quieter, and the expected ping never arrived. The return volley, challenging the poster child. While the bullet overlay toured conferences, another merger refused to salute. Abell 520 showed lensing mass where the hot gas piled up, a dark core that didn't track the galaxies. If the bullet was a sword, this looked like a shield raised at the last second. Stakes first. If offsets aren't universal, if some collisions put mass with galaxies and others glue it to gas, then the slogan "direct proof" turns into case by case. That doesn't kill dark matter. It kills the idea that one poster settles the physics. Every exception reopens the door MOND's camp kept wedged with equations and dates. Action turned technical fast. Teams reprocessed Abell 520 with deeper shape catalogs, tighter photometric redshifts, and alternative mass reconstruction priors. One group said the central peak was a smoothing artifact. Another, with independent data, found the core persisted. Meanwhile, simulations crafted off-axis collisions, triaxial halos, substructure flybys, and projection tricks that could sculpt confusing maps. You could make weirdness, but you paid for it with fine-tuned orbits and careful viewing angles. Microstory. A lensing student watched their mass peak march a few arcseconds with every tweak to the source redshift prior. They pinned the prior before unblinding and wrote in the lab book, "No more nudges." The peak stayed near the gas. Their advisor nodded, uneasy. In the next building, a theorist wrote "nonlinearity plus external field" on a whiteboard and drew an arrow from gas to potential. The arrows didn't feel like proof. They felt like homework. El Gordo entered like a heavyweight, a high redshift merger with big lensing power and offsets more bullet-like. But its required halo concentrations pushed lambdictum toward the tail of distributions. Observers added caveats. Line-of-sight structures can boost convergence. Mass sheet degeneracy can skew inferences. X-ray temperatures can mislead hydrostatic mass estimates. One-liners for press don't survive these footnotes. Proposals do. Here's the pivot that mattered. A few groups published pre-registered lensing pipelines for mergers, fixed shear calibration methods, fixed background galaxy cuts, predetermined smoothing kernels, and blind-done-blind procedures. They posted target lists and acceptance criteria before the first code. The question changed from which story is prettier to which prediction survives the freeze. It sounds boring. It's the only way to earn trust. Now the human beat. A communications officer kept consistent with in a headline after 3 drafts. A department chair moved a modified gravity debate from the sleepy last session to mid-morning and told both sides to show pre-announced targets. A grant panel split a block of time, half to extend a proven Halo simulation suite, half to a risky Abell 520 reanalysis with frozen priors. In the margin, someone wrote, "We'll take the heat if null." Meanwhile, MOND's relativistic cousins took their own swing. In TVS-like models, lensing potentials can shift due to field nonlinearity and environment, even when baryons sit with shocked gas. Add a small admixture of unseen but ordinary components, intracluster light, cold clumps, and you can move peaks. Critics said the elegance was leaking away. Defenders replied, "Elegance without predictions is a vibe. We posted kernels. Tell us where they miss." Abell 520 didn't become a knockout. It became a wedge. It forced people to say population with a straight face and to publish scatter instead of posture. Surveys compiled merger samples and asked, how often do we see bullet-like separations versus dark core anomalies, given realistic noise, projection, and modeling? Lambdictum expected a distribution with bullet-like cases common, messy ones rarer but real. Modified gravity frameworks posted which geometries should yield which offsets, and when they shouldn't, then lived with the misses. Microstory. After a talk, a senior cosmologist admitted to a grad in the hallway, "I still think halos are real, but Abell 520 means I don't get to call it case closed anymore." The grad shrugged. "I just want the priors locked." That's the generational shift in one exchange. Impact settled into culture. Fewer slides declared victory. More plots showed error bars you could park a bus in. Reviewers started insisting that merger analyses list blind choices up front and lock them. Press offices learned to keep consistent with in paragraph 1, not 4. The bullet stayed powerful, but it stopped being a cudgel. And here's the quiet twist you feel more than here. The more clusters demanded nuance, the more the field looked elsewhere for arbitration. If halos are real, we should meet the particle. If halos are bookkeeping, modified dynamics should pre-call galaxy-scale wiggles and lensing delays, no edits after unblinding. Basements got quieter, telescopes got sharper, the scoreboard waited. While posters argued, detectors in the dark kept asking the same question with colder xenon and stricter priors, and getting the same answer: silence. Chasing a ghost, the particle that never shows. While posters argued in the sky, basements learned patience. Stakes first, billions of dollars, thousands of careers, and a promise the public has heard for 40 years. If halos are real stuff, sometimes they should bump into us. Not often. Just enough to leave a tiny recoil, a brief flash, a clean excess above background. If that bump never comes, the story phrase, how long do you fund a ghost? Action moved underground. In a South Dakota mine, Lux then LZ chilled liquid xenon until the room sounded like a refrigerator in winter. Xenon 1T became Xeno NNT, Pandax expanded in China, DEAP watched Argon in Canada, Darkside ran in Italy. They wrapped tanks in water and rock, vetoed cosmic rays, counted photons in the quietest rooms humans can build. Each run tightened the cross-section limits on vanilla WIMPs, those weakly interacting massive particles that were supposed to be the obvious answer around tens to hundreds of GeV. The rectangles on log plots shrank. The signal region where theorists like to live got carved away. Meanwhile, on the surface, the Large Hadron Collider looked for missing energy, proof that something invisible flew out of collisions. Supersymmetry, the elegant theory that once promised a natural partner for the Higgs and a dark matter candidate for free, kept moving into corners of parameter space. Searches accumulated, exclusions stacked, and the clean discovery didn't land. SUSY stopped feeling inevitable and started feeling optional. Axions took the mic. If the galaxy bathes us in featherweight particles, a tuned microwave cavity under a fierce magnetic field can convert them into detectable photons. ADMX swept frequencies like scanning a radio dial in the dark. New haloscopes joined, dish antennas appeared, nuclear magnetic resonance techniques chased different couplings. Hints flickered, an excess here, a seasonal wobble there, then dissolved under better calibrations. The bar for "we found it" rose, and to their credit, teams raised with it. Here's the sting. Every null result was good science. It told us what dark matter is. It drove cleaner detectors, smarter background models, and tech that spilled into medicine and materials. But every null also moved the goalposts. If not WIMPs, maybe ultralight fuzzy fields that act like waves. If not cold and collisionless, maybe self-interacting, warm, or hidden in a dark sector with its own forces. The theory space blossomed into a zoo, great for creativity, brutal for a clear target. One graduate joked their thesis was how to look for what might not want to be found. Micro story. 2 students watched the run dashboard at 3 a.m. A blip rose just above threshold, exactly where a candidate might live. Heart rate spiked. Someone texted the Pi and headphones came off to hear the room breathe. By afternoon, a revised background model folded the blip back into noise. In the logbook, one of them wrote, "Expected signal never arrived." It became a mug in the break room. The joke got funnier because it hurt. Meanwhile, astronomy crowded the sidelines with demands. If cold, collisionless particles fill halos, we should see certain fingerprints, steep cusps in dwarf centers, a specific distribution of satellite galaxies, subhalo flybys leaving gaps in stellar streams, a neat concentration, mass relation. Observers found cores more often than cusps, planes of satellites that looked too organized, and streams whose gaps could be made by bar resonances as easily as subhalos. Simulations answered with baryonic feedback, supernovae, black hole winds, bursty star formation, puffing out cores and stirring satellites. Sometimes it worked, Sometimes the recipe list looked like a chef improvising after seeing the dish. Here's the human pivot. Funding committees started hedging bets with multi-messenger strategies: direct detection underground, indirect detection in the sky, collider searches on the surface. Fermi and HESS stared at the galactic center for annihilation signatures. AMS-02 measured cosmic rays with exquisite precision. Excesses came with caveats. Caveats ate the excesses. The scoreboard stayed stubbornly blank. And that silence did something awkward to the culture. It made modified dynamics sound less like heresy and more like a necessary backup plan. Not a victory lap, an exit door that had to be kept unlocked. Superfluid dark matter tried to live in both worlds. A particle that condenses into a superfluid in galaxies and mediates a MOND-like extra force, while behaving collisionlessly in clusters and the cosmic web. Emergent gravity ideas suggested the dark pull might be a thermodynamic response of spacetime tied to cosmic expansion, with a particle layered on top to match the early universe. Hybrids stepped forward, promising galaxy-scale regularities without abandoning the CMB's precision. Microstory. A postdoc drafted a grant titled 5 Nails, each a falsifier. Bar pattern speeds a superfluid must predict. A strong lens time delay an emergent kernel must miss if wrong. A dwarf's outer rotation points a MOND interpolation must hit with frozen parameters. A stream gap rate a clumpy halo must produce. A senior warned, if you miss 3, you're done. The postdoc said, if I don't risk missing, I'm done anyway. The panel funded half. It was more than they expected. Meanwhile, JWST made the quiet rooms feel louder. Galaxies at Z greater than 10, some compact, some surprisingly ordered, showed up earlier than comfortable lambdictum assumptions predicted without retuning star formation physics. If gravity gets a low acceleration boost, early structure grows faster. If not, feedback dials twist again. Either way, the particle didn't help here. It only mattered if it could seed and scaffold exactly on time. Here's the direct address. You're allowed to ask, where's the particle, without being anti-science. You're allowed to ask, where are the time-stamped galaxy predictions, without being anti-consensus. Tie your trust to who posts risks before data and lives with misses. Impact? The underground silence didn't kill dark matter. It humbled it. It pushed the story toward hybrids and protocols, away from vibes and after-the-fact fits. It set the stage for the next arbitration. Not posters or pings, but clocks and environments. Tests that neither story can sweet-talk after unblinding. JWST opens the curtain, the too-early universe. The email ping started before sunrise. A Pi opened a candidate list and stopped breathing for a beat. Redshift stacked past 10. Another message arrived. Compact, bright, organized. Not toddler galaxies. Teenagers showing up to kindergarten. Stakes first. Lambdictum sets the pace. Dark matter scaffolds early, but baryons take time to cool, collapse, and settle. If disks and dense nuggets appear within the first 500–700 million years, Z greater than 10, either baryons cheated or gravity fed structure faster than the standard timeline allows. That's not a tweak. It's a stress test on the backbone. Action spilled across Slack channels. JWST's NERCam pulled deep fields. Photometric redshifts piled up at values we used to whisper about. Teams flagged candidates. CERS 93316, bright siblings near GNZ11's neighborhood, objects flirting with Z12. Spectroscopy stepped in, trimming pretenders, confirming a solid population that still sat too early for comfort. Some systems looked compact and quiescent when quiescence shouldn't exist. Others hinted at ordered rotation, velocity gradients that didn't scream chaos. Dust and metals flashed in spectra, implying rapid star cycles. If you were counting on turbulence and mergers to dominate, the sky asked for a rewrite. Meanwhile, caution pressed its hand on the table. Photometric redshifts can be fooled. Nebular lines inflate fluxes. Initial mass functions tilt mass estimates. Pipelines updated. Some jaw-droppers moved down in redshift. But the pile didn't go away. The center of gravity stayed beyond 10. The problem wasn't one celebrity galaxy, it was a census leaning older than expected. Here's where the human angle bites. A simulation lead stepped up at a conference and said, "We can match the counts if we dial star formation efficiency up early." An observer replied, "We can lower masses with a top-heavy IMF, but the kinematics still look settled." The room laughed and winced. Everyone knew the game. Fix one axis, break another. Make the early number count sing and the size-mass relation cracks. Protect sizes and reionization budgets wobble. Keep reionization tidy, and late-time stellar mass functions complain. Lambdictum didn't fold. Modelers added bursty modes, cold streams, clump-driven inflows, stronger cooling in metal-enriched pockets. Some runs produced early disks and compact nuggets, but the juggling felt tight. One misstep and a later observable slipped. The claim became possible with tuned physics, not natural from first principles. That matters for trust. From the MOND side, the tone was different. Low acceleration boosts kick in sooner for tiny halos on the cusp of binding. In that picture, gravity acts a little stronger right where early structures need help. Coherence arrives earlier, rotation settles faster. You don't need as much invisible scaffolding to herd baryons into order. That doesn't solve everything. Cosmology is still heavy lifting, but the trend lines leaned their way. It wasn't a victory lap. It was a raised eyebrow that said, "We told you to watch the pace." Emergent gravity ideas took their shot too. If the scale ties to c times the Hubble rate, the early universe's higher h might tilt the elastic response of spacetime more strongly. That's abstract until you write numbers. A team posted an emergent kernel and pre-registered predictions. Given baryon maps, here are rotation speeds and lensing profiles we expect for a handful of high-Z disks. No moving goalposts after spectra land. It sounded risky. It sounded like science. Microstory. A time allocation committee split a night between flashy new fields and boring confirmation. One panelist argued for fresh candidates. Another said, "We need stakes. Approve programs that can falsify." They funded deep spectroscopy on a small set of Z greater than 10 disks with pre-announced velocity targets. In the minutes, someone wrote, "No retuning allowed." Meanwhile, reionization watches the clock. If early galaxies are more numerous and efficient, ionizing photons may clear the fog faster. Teams updated Feynman luminosity functions. Escape fractions got debated. 21 centimeter surveys sharpened constraints. Lambdictum can flex, tune efficiencies without breaking the CMB's integrated optical depth. MOND-flavored stories can claim that earlier coherence helps photons leak. Either way, the sky forced both camps to put dates and numbers on their claims. Here's a direct address. When you see universe forms galaxies too early, ask two questions. Did spectroscopy confirm those redshifts? And did the team pre-register their mass and kinematic inferences? If a plot looks perfect after 3 pipeline versions, check how many knobs moved. Back to people. A grad taped 3 lines above their desk, predicted rotation speeds for 3 high-Z disks posted before observations. When the first spectrum arrived, the line sat close. Not perfect, close enough to matter. They wrote the date next to the miss and didn't touch the kernel. Their advisor said, "Leave it. That's what credibility looks like." Impact settled in the culture. Reviewers started asking for pre-registered high-Z modeling choices. Journals nudged authors to separate postdictions from predictions. Press offices kept consistent with in the first paragraph. The headline stayed punchy. The caveat didn't get buried. And the quiet twist, early structure didn't just stress lambdictum. It also pinned modified ideas to the mat. If you claim a faster early pace, you have to survive size, mass, metallicity, and kinematic checks without magic. If you claim lambdictum can get there, you can't break late-time wins to do it. The scoreboard demanded both sides risk numbers. So where does that leave us? With dates on the margin, high-Z disks turned into clocks. Their rotation speeds, sizes, and metals measure how fast gravity feeds order. If invisible scaffolding is real, the particle still owes us a meeting. If gravity shifts at low accelerations, it owes us more than poetry. It owes us plots we can't unsee. Everything was about to get even more concrete. Clocks in lenses, puffball galaxies under environmental pressure, and local clusters flirting with a threshold. Tests that write verdicts in ink. Gravity as emergent, new rules beneath the law. To understand why that stubborn Escale might know the universe's pace, we don't start with galaxies, we start with information. Get this, what if gravity isn't fundamental but a large-scale habit that emerges from microscopic degrees of freedom? Not a new force tacked on, but geometry as bookkeeping for hidden states we never see directly. Stakes first. If gravity is emergent, part of what we've labeled dark could be an elastic response of spacetime itself, a memory effect tied to horizons and entropy. That reframes the hunt. Instead of chasing a particle to fix galaxy curves, we'd need the rule that turns information into pull, and it might naturally grow stronger at low accelerations. Action begins with a weird result from the 199s. Ted Jacobson showed you can derive Einstein's equations from the first law of thermodynamics. Imagine a local horizon, like a tiny black hole edge for an accelerated observer, where heat flow across the surface and changes in entropy balance. Demand that balance everywhere, and general relativity drops out. Gravity as an equation of state, not a starting axiom. Layer and Bekenstein-Hawking. Black holes carry entropy proportional to area, not volume. Information clings to surfaces. Then holography arrives. T. Hooft and Susskind argue the physics in a region can be encoded on its boundary, like a cosmic hard drive with capacity set by area. In toy models, the AD-SCFT duality maps gravity in a bulk to a quantum field theory on a boundary. Our cosmos isn't AD-S, but the lesson's loud. Geometry and information are two sides of the same page. Now Verland walks in and says, if information has entropy and spacetime has horizons with temperature, forces can look like entropic tendencies, systems pushing to maximize microstates. He sketched how Newton's law can arise as an entropic effect near a holographic screen, pushed to a universe with dark energy, de Sitter space, and an extra, elastic-like response appears on large, low-acceleration scales. In galaxies, that response can mimic dark pull tied to the baryons and the cosmic horizon. The scale pops out with the right order of magnitude, whispering that c times the Hubble rate isn't a coincidence, it's the thermostat. Meanwhile, observers did the only fair thing. Numbers, not slogans. Teams took emergent gravity prescriptions and asked whether lensing around galaxies, rotation curves, and the baryonic Tully, Fisher slope and scatter line up. Some fits looked promising. Others missed by factors you can't hide in error bars. Without a crisp microscopic model in de Sitter space, the real universe, emergent gravity risks becoming a metaphor with math. Here's the checklist that formed in seminar rooms. Recover Einstein where fields are strong, reproduce MOND-like scaling in disks, bend light correctly, play nice with the CMB's acoustic peaks, make predictions you timestamp before data. Gates 1 and 2 looked within reach. Gates 3 and 4 are where most efforts tripped. Light bending is geometry. The acoustic peaks are fossil sound waves. You don't get to repaint them without paying everywhere. Microstory. A young theorist drew a holographic screen on a whiteboard and said, if the extra pull is elastic memory, write the kernel that maps a baryon map to an acceleration field. Her advisor replied, then publish it before the lensing data lands. They did, listing specific edge-on spirals and strong lenses, posting code, freezing parameters. When the first lens unblinded, the delay was off by 15%. They didn't touch the kernel. They wrote miss, the next lens landed inside the band. They wrote hit. Credibility isn't a vibe, it's a ledger. Meanwhile, quantum information crept in with a different angle. It from Qubit sketches how entanglement patterns can literally stitch space. Tensor networks like MERA build layered webs where distance tracks how many bonds you cut, change the entanglement at low energy densities, and the emergent geometry changes its rules. Translated, in the low acceleration regime, inertia and pull could shift because the underlying information fabric responds differently. That's pretty until you need a kernel that predicts a dwarf's wiggle at 6 kiloparsecs, before you see the wiggle. Here's where culture meets calculus. A group posted an emergent kernel with one scale tied to the Hubble rate, no halo parameters, and a rule for lensing potentials that didn't cheat. They pre-registered 10 targets, 5 spirals with clean baryon maps, 3 strong lenses with long time delays, 2 dwarfs with extended gas. Acceptance bands froze. Misses would cut, hits would count. Reviewers grumbled. A journal accepted the protocol paper. The first dwarf came in hot. The curve sat high at large radii, the kernel underpulled by 10%. The team labeled it a fail and didn't add a term. 2 months later, an edge-on spiral landed almost dead center. A lens delay arrived just outside the band. The team posted why their kernel bent light too weakly where shear was high. No excuses. Notes for version 2, but only after the batch closed. Direct address. This is how you keep emergent gravity from turning into vibes. Freeze the math, name the targets, accept pain. If a theory won't risk a number, it deserves your skepticism. If it will and misses loudly, it deserves another round. Impact. Even partial wins matter. If an emergent kernel reproduces the radial acceleration relation slope and scatter from baryon maps with no halos, that's spinal. If it also lands lensing in a subset of clean systems, you've earned a seat at the table next to superfluid models and relativistic MOND. If it breaks on the CMB, you layer a particle for early times and own the hybrid out loud. Limitation acknowledged. We don't yet have the de Sitter dual we dream of, or a finished microstate model you can hand to a telescope. But the path exists, and the discipline, pre-registration, frozen priors, public code, keeps the promise honest. One more micro story. A committee asked a pi, what result kills your kernel? The pi answered with a specific lens, a delay number, and a tolerance. The room went quiet, the good kind. They got the time. That's how an idea stops being a poster and starts being a test. Everything tilts toward one rule. Stop explaining after, start predicting before. If gravity is emergent, it'll show up where accelerations go thin, in disks, in lenses, in streams, not as poetry, but as plots you can't unsee. The scorecard, predictive power versus patchwork. Here's where we stop cheering posters and start counting receipts. Predictions first, fits second. Who called what before the data landed, and who added dials after seeing the plot. Start small and sharp, disk galaxies. MOND walked in with 2 crisp tickets stamped decades ago. Ticket 1, asymptotically flat rotation curves no matter the size. Ticket 2, the baryonic Tully-Fisher relation, v to the 4th tracks total baryonic mass with tiny intrinsic scatter. Not fitted afterward, predicted from a single low acceleration scale. Observers mapped low surface brightness disks, gas-rich dwarfs, bright spirals. The slope, the normalization, the scatter. They hugged the line. Add the radial acceleration relation. At every radius, the observed acceleration ties to what you compute from baryons alone, bending right where that scale lies. Again, a rule first, data later. Meanwhile, lambdictum on the big canvas. The cosmic microwave background's acoustic peaks, baryon acoustic oscillations, growth of structure on 100 megaparsec scales, tight, interlocking winds with a compact parameter set. That coherence isn't marketing, it's hard-earned physics. You vary parameters inside narrow priors and hit independent datasets. Precision cosmology isn't a slogan, it's a belt of metals. So the scoreboard splits by scale. Galaxies favor predictive crispness. Cosmology favors ensemble accuracy. In the middle, dwarfs, satellites, ultra-diffuse galaxies. The noise is real, the modeling messy, and both camps sweat. Now the head-to-heads that matter. Take a spiral with a clean baryon map. MOND posts a rotation curve using one universal and a fixed interpolation, with stellar mass-to-light ratios inside pre-announced priors. Lambdictum posts a halo-based fit with concentration and normalization drawn from simulation-informed priors. In many disks, MOND's curve hugs the data with no halo gymnastics. Lambdictum gets there too by letting halo parameters dance, sometimes with feedback histories tuned to keep the line pretty. In a referee's margin that reads, MOND predicts, Lambdictum accommodates. Flip the ledger. MOND stumbles in clusters. Even with the boost, mass shortfalls persist, especially in cores. Add massive neutrinos or unseen baryons and you're back to layering components. Cosmology is heavier, nailing the CMB peak structure and late-time expansion without smuggling in dark by another name remains a hurdle. Relativistic completions like TVS help with lensing, then strain elsewhere. That's not disqualifying, it's a cost written in ink. Lambdictum small-scale bruises aren't rumors. The cusp core issue in dwarfs, too-big-to-fail satellites, thin co-rotating planes around the Milky Way and Andromeda that look rarer than Machs, ultra-diffuse galaxies with either suspiciously little or too much inferred dark matter. Simulations answer with subgrid physics, stellar feedback blowing out cores, bursty histories reshaping halos, environment pruning satellites. Sometimes they nail it. Sometimes the recipe list reads like explain after. The honest move is posting population predictions with error bands before surveys land. Here's the psychological snag, elegance versus coverage. MOND feels elegant in disks, one scale, one bend, tiny scatter. Lambdictum feels comprehensive, one framework stitching the early universe to today. Elegance tempts, coverage comforts. Neither should get a pass without time-stamped risks. So we write the scorecard like a lab protocol. Columns: phenomenon, prediction, posted date, free knobs, mistolerance, outcome. Rows: BTFR, slope and scatter, MOND posted, Lambdictum accommodates via feedback tuned populations. RAR shape, MOND posted, Lambdictum explains aggregate trends with baryon, halo coevolution. Cluster lensing, Lambdictum posted collisionless behavior. MOND relatives post offset patterns under defined geometries. Strong lens time delays, Lambdictum posts with halos. Emergent and MOND kernels post with frozen lensing rules. UDG external field effect, MOND posts environment flips. Lambdictum posts stripping formation distributions. Tidal stream gaps, Lambdictum posts subhalo encounter rates. MOND-like fields post smoother streams with distinct precession. Microstory, a journal editor insists both sides submit pre-registrations for a joint special issue. The MOND team lists 20 disks, a fixta, an interpolation function hash, and mass-to-light priors. The Lambdictum team lists a halo prior from a specific simulation suite, fixed feedback parameters, and a mock-to-real pipeline. The editor writes, no retrofits after unblind. The comments section turns into a scoreboard rather than a food fight. Another micro-story, a simulation pi emails, we matched the RAR's mean but overshot the scatter. The observer replies, we matched the MOND curve in 12 dwarfs, missed 3. Both publish misses in bold. It feels weird. It reads honest. Direct address. Tie your trust to the ledger. If a theory only sings after the plot is drawn, discount the harmony. If it posts a number, misses cleanly, and explains the miss without moving the line, that's maturity. Here's the pivot to stakes. Careers tilt toward accommodation because it guarantees a figure. Predictions risk a blank slide. We flip that incentive. Fund pre-registered nails, reward clean nulls. Then the scorecard turns from vibes into verdicts. Next up, people who bet their names on numbers they couldn't edit later. Predictions decide careers, and who dares to make them. The people who wouldn't bend. While the scorecard asked for numbers, rooms full of people had to decide if they'd risk them. Stakes first. Tenure clocks, grant renewals, and reputations that take 10 years to build and 1 sentence to dent. Picking the clean story meant safety. Picking the messy truth meant sleeping less and explaining more. Vera Rubin set the tone without theatrics. She kept the plot simple. This is what we observe. In private, she told students, write what the sky says. No victory laps, no world-saving rhetoric, just a steady refusal to pad the curve with a narrative it hadn't earned. That restraint became armor. You could disagree with a model. It was harder to dismiss a sentence that honest. Mordehai Milgrom carried the other kind of stubborn, quiet, severe, all in the equations. He wrote a single scale in 1983 and let the sky judge it. Years of jokes didn't budge him. When a fit landed, he time-stamped it. When clusters strained the story, he worked on relativistic spines instead of pretending the bruise wasn't there. Persistence isn't loud. It's returning to the same chalkboard after everyone else went to lunch. Microstory. A postdoc presented MOND predictions for low-surface brightness galaxies with one fixed and a locked interpolation. A senior shot a volley distances, inclinations, warps. She clicked to pre-registered cuts and code links. The room went quiet because the usual escape routes were sealed. After the talk, that senior sent a 2-line email. I disagree with your premise. Your DDO 154 outer points are annoyingly good. She printed it and taped it in a drawer. Choices went the other way too. A grad student deleted MOND from a title to dodge a hostile referee, kept the plot and got the paper through. It felt like a tiny lie. It bought them another year of research. In a different building, a PI delayed an external field prediction until after job interviews, then posted the preprint with frozen priors and a target list. They called the delay prudence and the pre-registration penance. Press offices wrestled in softer ways. A scientist wrote, consistent with, into a cluster release. The comms officer cut it to direct proof to land a headline. The scientist argued, the edit stuck. A year later, after enough blowback, the same officer fought to keep consistent with in paragraph 1 and 1. That small victory changed how 1,000 teachers' slides would read. Referee rooms had their own gravity. A relativistic MOND lensing paper got incomplete without cosmology, while a new subgrid feedback recipe in lambdictum earned, promising future work can address the mismatch. Same distance to the finish line, different patience. A panelist said out loud what many implied. We punish incomplete frameworks more than incomplete patches. Nobody wrote that as policy. It behaved like one. Microstory. A young observer proposed a clean falsifier, strong lens time delays with a pre-published kernel, no retuning. A reviewer asked for flexibility to ensure success. The PI replied, success is a miss we can't explain away. The committee funded half the time and underlined, publish nulls. The team framed the printout and hung it next to the coffee machine as a dare. There were apologies too, small and expensive. A senior who'd mocked a dwarf prediction years earlier found the new data sitting on the pre-published line. In the hallway, he told the grad who'd asked the hard question back then, I was wrong about that galaxy. No ceremony, no pivot to, but. He walked into the next seminar with one more question he hadn't planned to ask. Culture bent where people made rules. A survey PI carved out hours for an external field test in ultra-diffuse galaxies and wrote into the call, nulls are deliverables. A journal editor required pre-registrations for a special issue and banned retrofits after unblinding. A department chair moved a modified gravity session out of the graveyard slot and told both camps to bring predictions with dates. Direct address. This is what courage looks like in practice. Freezing parameters you'd rather wiggle, publishing misses in bold instead of burying them in supplements, saying the number that could cost you a citation and then living with it. It's not rebellion for clicks. It's the discipline that keeps science from voting on the truth. Microstory, a Slack channel pinned no moving goalposts before telescope night. A new preprint dropped with a tweak that would prettify their curves. Someone typed, we could adopt it. The PI wrote, we said no. The team pushed the commit hash to the top of the doc and unblinded anyway. 2 misses, 1 hit. They kept the misses on slide 1. These people didn't topple a paradigm by force. They made it earn its keep. They wrote the tests as nails, not ornaments. They accepted that a clean fail is a kind of win, and they gave you a way to track the truth without picking a tribe, dates on the margin, knobs that don't move, and plots that speak before the captions do. Pillar 10, the tipping point tests. We'd reached the place where arguments need clocks, not charisma. Stakes first. Tests you can pre-register, freeze, and fail in public. No halo retuning after the fact. No new interpolation functions smuggled in at the 11th hour. If these land cleanly, one camp loses a crutch. If they split, the hybrid world steps out of theory and into schedules. Start with the puffballs, ultra-diffuse galaxies. They look like cotton candy, huge, faint, barely holding together. In lambdictum, you can get both low dark and high dark flavors through halo diversity, stripping, and formation history. In MOND, there's a sharper bet, the external field effect. Put a UDG deep inside a cluster's gravitational field and MOND says the internal boost gets suppressed. Push it to the outskirts and the MOND boost returns. That's a date-stampable prediction. Action moved to catalogs and slits. Teams pre-registered samples. UDGs within defined projected radii of clusters. Control UDGs in the field. They froze cuts on surface brightness, distances, and contamination. They planned to trace kinematics with planetary nebulae and globular clusters as test particles, posted target lists, and locked acceptance bands. The promise read like this: cluster-adjacent UDGs should look dynamically light under MOND, field UDGs heavy. Lambdictum said environment matters too, but predicted a different distribution across radius and infall history. Microstory. On a whiteboard, a grad drew two histograms and wrote inner and outer. Their pi circled the overlap and said, "This is where we live or die." Months later, the first points dropped. Some inner UDGs looked lighter than lambdictum median expectation and within MOND's suppressed band. Others looked too heavy for either. The team kept the priors frozen and posted the misses in red. That's the point, no moving goalposts. Meanwhile, closer to home, Gaia turned star clusters into seismographs. Open clusters live near the threshold in their outskirts. If MOND's low acceleration rule bites, velocity dispersion should bump slightly beyond a few parsecs, modulated by the Milky Way's external field. Newton says they shouldn't. Groups pre-registered membership cuts, binary contamination models, and error floors. They wrote down dispersion versus radius predictions, with the interpolation function hash baked into the PDF. Action hinged on proper motions whisper-thin. One cluster showed a gentle uptick right where the internal acceleration crossed another sat flat within uncertainties. The protocol held. No new binaries invoked to smooth a bump after unblinding. No revised distances to conjure one. Each cluster tightened the band. Nobody got to cherry-pick. The ledger grew. Now the cleanest clocks, strong lensing time delays. Quasar light that takes multiple paths around a foreground galaxy arrives out of sync. Those delays depend on the gravitational potential depth along each path. Lambdictum fits are baryons plus halos with priors from simulations. Modified gravity and emergent models must specify how they bend light where they boost dynamics. No cheating with two different rules. Teams did it right. They published lens lists, monitoring baselines, velocity dispersion priors, and, crucially, fixed lensing kernels for MOND-like and emergent frameworks. No retrofits. The first batch came back mixed. A few lenses fell neatly into lambdictum bands. One landed inside an emergent kernel band that predicted a deeper potential from baryons alone. Another sat between both, demanding cleaner shear estimates. The story didn't crown a winner. It cracked the habit of infinite hindsight. Tidal streams added a different lever. In lambdictum, subhalos pepper the Milky Way and kick streams like GD1 and Palomar 5, carving gaps with predictable rates and sizes. In MOND-like fields, there's less small-scale clumpiness, different precession, and smoother ribbons. Teams pre-committed to gap detection thresholds, background models, and mock injection tests. Early runs saw fewer clean, sharp gaps than the coldest lambdictum mocks predict, but enough structure that featureless wasn't honest. Warm dark matter, baryonic bar resonances, a modified field. The acceptance bands forced everyone to print their priors next to the plot. Microstory, a stream analyst hovered over a suspicious gap, tempted to lower the threshold by a hair. They didn't. The gap failed the pre-registered cut and went into the supplement as not counted. In a separate Slack, someone typed, "We'll get roasted." The Pi replied, "We'll get trusted." Planes of satellites brought the population angle. The Milky Way and Andromeda show thin, possibly co-rotating planes of dwarf companions. Rare in lambdictum but not forbidden with filamentary infall. More natural in long-range modified dynamics where the external field can shepherd orbits. A consortium locked a planarity statistic, built survey-realistic mocks, and registered an analysis window. If observed frequencies sit far above mocks, lambdictum takes a bruise. If selection effects wash it out, MOND loses an easy talking point. The window is open. The referee letter that once said "too messy" now says "we'll wait." Direct address. This is where you watching get a play scorekeeper. Pick one test, UDGs under the external field, Gaia cluster dispersions, lensing delays, or stream gaps. Write down the date of the prediction and the knobs that were frozen. When the results land, check. Did anyone touch a dial they promised not to? If yes, ask why in public. Here's the pivot. These tests don't just choose a camp. They map the hybrid space honestly. A warm or self-interacting dark sector might blunt stream gaps but leave lens delays. A superfluid phase could mimic MOND in disks yet act collisionless in clusters. An emergent kernel could nail the radial acceleration relation while needing a particle for the CMB. The tipping point isn't one knockout. It's a pattern that forces honesty. Everything was about to feel even less comfortable and more useful because the habits that turned a placeholder into dogma were standing in the way. The next act names them and breaks them. The cover-up without emails. Here's the turn most people dodge. You don't need a memo to bury doubt, you need habits. Stakes first. When institutions reward the clean story and punish the messy one, a placeholder can harden into truth without anyone deciding to lie. That's the soft cover-up, choices that make the bandage easier to love than the wound. Start with path dependence. The first cosmology codes that matched clustering used cold dark matter. Those codes became toolkits. Toolkits trained students. Students wrote the next generation. Homework problems assumed halos. Textbooks sketched tidy formation trees. A young observer learns to decompose curves into bulge, disk, gas, halo. If a galaxy doesn't fit, tweak the halo. That's not deceit. That's muscle memory. Meanwhile, press offices hunt headlines. Consistent with doesn't travel, direct proof does. A scientist writes, lensing offsets consistent with collisionless mass given reconstruction assumptions. The comms officer trims to fit a column, dark matter seen separating from normal matter. The nuance survives in paragraph 4. The world reads the headline. A teacher downloads the image and never sees the footnote. Nobody plotted to mislead. The sentence just got cleaner and truth got thinner. Funding follows deliverables. Big surveys promise 10 plots and 5 subfields. Lambdictum stitches those promises together, so proposals wrap around it. A risky MOND test with frozen priors might fail and produce one short paper with a no. A safe halo calibration project generates a steady stream of progress. Panels are told to protect outcomes. The risky ask gets a polite paragraph and a partial award. The safer one gets a full block and a pat on the back. That's a choice, not a conspiracy. Referees write culture in the margins. A relativistic MOND lensing paper gets incomplete without full cosmology. A new lambdictum subgrid patch gets promising, future work can address the mismatch. Same distance to completeness, different patience. A panelist says it out loud. We punish incomplete frameworks more than incomplete patches. No policy memo, just a weight that always leans the same direction. Microstory, A grad student submits external field effect in UDG's pre-registered predictions. Reviewer 2 writes, "Interesting but controversial, please reframe in standard terms." The student changes the title to Environmental Dynamics in Ultra-Diffuse Galaxies, leaves the predictions intact, and gets accepted. They didn't hide the result, they hid the word. That's how a lie by omission learns to walk. Another one, a PI drafts a press release with consistent with underlined 3 times. The comms officer deletes it. The PI argues. The officer says, "We'll lose readers." They compromise. The phrase moves to paragraph 2. That small win keeps uncertainty in the first screen of 1,000 phones. It also costs a little attention. The trade becomes a habit, clarity, or clicks. Path dependence shapes what feels real. Halo concentration sounds like a property of nature, not a parameter. Subgrid feedback sounds like physics, not a knob. Students absorb the nouns. When they ask, "How many recipes are we allowed to add?" the answer is, "As many as the data demand." That's professional. It's also how a patch becomes a pillar without passing through pain. Microstory. A time allocation committee weighs 2 proposals. One extends a simulation suite that already matches a known relation. The other pre-registers a MOND kernel lensing test that could fail loudly. The chair asks, which moves the field if it fails? Silence. They split the night. The safer program gets the lion's share. The risky one gets just enough to claim they tried. Everyone goes home believing they were fair. Textbook inertia locks priors. A chapter from 201 still shapes 2026 lectures. The alternatives live in a sidebar. Controversies. MOND gets 3 paragraphs. Emergent ideas get a sentence. Not because authors hate risk, because adoption cycles lag and teachers need stable syllabi. By the time students meet research papers, the default feels like gravity itself. Here's the direct address. This is not a cabal, it's comfort. It's clean figures over risky forecasts, headlines over hedges, patches over frameworks. The result reads like intention. It's not. It still buries doubt. So how do you break it? You change the incentives. Pre-registration of predictions, targets named, priors frozen, code posted, turns hindsight into risk. Journals that reward nulls make clean no a publishable success. Panels that carve out budget for falsifiers force fields to accept pain on schedule. Press offices that keep consistent with in paragraph 1 retrain the public to spot caveats without turning away. Microstory. A journal editor launches a grav trial track. Authors must submit a protocol first. Knobs listed, targets named, acceptance bands fixed. Retrofits after unblinding require a tuning badge on the first page. A reviewer protests. The editor says, "We're done measuring flexibility." The first issue publishes 2 misses in bold. It gets fewer clicks and more bookmarks. Another, a survey PI, writes into the call, "Nulls count. We will publish failures as headline results." A postdoc circles nulls count on the printout and tapes it above their monitor. 6 months later, their cluster sample returns flat. They publish anyway. The abstract reads, "Prediction failed." The citation count is modest. The trust count in the room goes up. Here's the pivot. Once a few labs live like this, the soft cover-up loses oxygen. The bandage has to earn its place every cycle. Modified ideas do too. Nobody gets to slip a new knob in after the fact and call it progress. The story stops voting on truth and starts betting on it. One last direct hit. If you run a lab, a panel, a journal, or a press office, write 1 sentence you'll keep. "We accept a clean failure as a success." That's the only policy that matters. That's how a placeholder stops pretending to be the law. Building a better gravity, the hybrid frontier. Tear off the bandage, then don't bleed out. That's the brief. We keep Cosmology's medals, we earn galaxy-scale regularities without after-the-fact acrobatics, and we post risks in ink. Not slogans, engineering. Start with relativistic MOND. Bekensten's TVS gave a spacetime where light bends with the same rule that boosts dynamics at low accelerations. Later builds trimmed and swapped fields, but the recipe stayed. Einstein in strong fields, a controlled morph near a lensing computed, not hand-waved. On disks, you inherit MOND's sharpness, rotation curves from baryon maps with one universal scale. On cosmology, you mimic lambdictum background with an extra field that looks smooth early. The bill is obvious. Every auxiliary field adds parameters. You pay in elegance to buy reach. Meanwhile, superfluid dark matter walked in from the lab vibe with a two-faced trick. Let dark matter be a particle that condenses into a superfluid in galaxy cores. The phonons in that superfluid mediate an extra force that reproduces MOND-like scaling for stars and gas. Outside, clusters, cosmic web, no condensate. The stuff behaves collisionlessly and carries lensing mass. One component, two phases. Cosmology stays lambdictum-like. Disks obey the low acceleration law without halo contortions. Here, why this isn't just a nice story. You can post date-stamped bets, bar pattern speeds, disk stability thresholds, rotation curve residuals tied to baryon clumps before the spectra land. Emergent plus particle hybrids push from the other side. Keep a particle sector to honor the CMB and large-scale growth. Layer an emergent kernel derived from spacetime's elastic memory to map baryon geometry to an extra acceleration in the Loa regime. The scale ties to the Hubble rate, the kernel ties to the baryons. On small scales, the kernel dominates. On large scales, particles rule. The prize is a reason for the tight galaxy relations, not a retrofit. Here's the protocol that turns hybrids from vibes into tests. Freeze the knobs once. For superfluid DM, fix particle mass, self-interaction, and coupling. For TVS-like builds, fix the interpolation and lensing fields. For emergent kernels, fix the functional form and its one scale. Publish the hashes. Pre-register targets. Named disks with clean baryon maps. Specific strong lenses with time delays and stellar dispersions. A cluster set with X-ray and SZ profiles. And a UDG sample across environments. Post acceptance bands before data. Misses get labeled fail, not calibration. Microstory. A team in a chalk-dusted room writes no tuning after unblind above a list of 5 nails. Nail 1. NGC 6946's bar pattern speed. Superfluid model must land within 10% using the fixed coupling. Nail 2. A clean lens time delay system where the emergent kernel predicts a 6% deeper potential from baryons alone. Tolerance plus or minus 8%. Nail 3. A UDG in the inner coma region, MOND-like external field suppression must push its dispersion below a posted band. Nail 4. Palomar 5 stream gap rate, lambdictum subhalos must dent it at the pre-registered threshold. Nail 5. A cluster pressure profile, superfluid fraction must be negligible within posted radii. They sign the list, post the code, and go home uneasy. Good. Meanwhile, instruments are finally serving the menu. Meerkat and NGVLA feed razor-sharp HI maps. ALMA locks molecular gas. Muse and KCWI map ionized flows. Long baseline monitoring nails lens delays. EROSITA and ACT polish cluster pressure profiles. Gaia's Doctor 3 turns outer disk motions and streams into dynamical seismographs. The data firehose no longer rewards flexibility. It punishes it. Direct address. This is where you get to watch ideas earn oxygen. When a superfluid model posts a bar speed and lands it, it buys trust. When it misses and resists adding just one coupling, it buys more. When an emergent kernel posts a lens delay and whiffs, then waits until the batch closes to revise, that's credibility. If a TVS-like build nails a lensing mass map in a dense baryon lens without halos, that's a receipt. If it breaks the CMB, it must say hybrid out loud. Here's the live example. A superfluid team froze parameters and posted predictions for 4 galaxies with measured bars. 2 landed inside tolerance, 1 missed high, 1 missed low. They labeled the miss, didn't touch the dials, and wrote version 2 after batch. An Emergent group posted 3 strong lens kernels. One nailed a delay, one underpulled in high shear, one sat on the edge. They kept fail on slide 1. A TVS variant matched a dwarf's curve and a lens shear profile, then stumbled on a cluster's core mass. They added needs auxiliary mass in clusters to the abstract, not the supplement. Micro story. A grant panel reads 3 protocols. They circle the one that says nulls are deliverables and fund it first. The safer simulation extension gets money too, paired with a requirement to pre-register small-scale predictions. The chair writes, no more scorekeeping with hindsight. Limitations. Hybrids can bloat if you let them. That's why the protocol matters. Freeze the knobs, accept pain, publish code, name nails with dates. No discovering priors after unblinding. That's the culture shift that drains the cover-up without emails. So the frontier isn't a truce, it's a trial. Keep lambdictum big canvas wins. Earn MOND's disk sharpness. Let superfluids, TVS-like spines, and emergent kernels compete on posted risks. Then let clocks, streams, bars, and UDGs write the verdicts in ink. What this means for you: reality, risk, and wonder. Here's where the story leaves labs and lands in your hands. Stakes first. This isn't just about galaxies. It's about how you decide what's real when experts disagree and headlines sell confidence. If gravity bends at low accelerations, your sense of certainty bends with it. You live on provisional promises, GPS timing, medical imaging, weather models. When a promise expires, do you double down or do you ask for receipts? Start simple. Tie your trust to method, not tribe. The clean method is this: predictions posted before data, knobs frozen, code public, misses printed in bold. If a team won't risk a number, discount their story. If they risk it and miss without moving goalposts, count that as courage. If they land it, let the wind move you more than a tidy plot drawn after the fact. Direct address. You're allowed to like lambdictum medals and still ask, where's the particle? You're allowed to admire MOND's disk precision and still ask, where's your cosmology? You're allowed to enjoy emergent gravity's poetry and still say, numbers please. You're not being cynical. You're setting terms for trust. Here's what to watch next without a telescope. Pick a date-stamped nail. Ultra-diffuse galaxies near clusters. MOND's external field predicts environmental flips. Lambdictum predicts a different distribution tied to stripping and infall. The cuts and acceptance bands are posted. Strong lens time delays. Modified kernels have frozen their rules. Lambdictum uses halos with simulation priors. Delays are clocks that don't care about vibes. Gaia open clusters. Dispersion bumps at the threshold either show up or they don't. Membership cuts and binary models are pre-registered. Tidal stream gaps. Subhalo encounter rates versus smoother, differently processing streams. Thresholds are locked. Write one down. When the result lands, check whether anyone touched a dial they promised not to. If yes, ask why out loud. Human angle. A grad tapes 3 plots above their desk. A BTFR line labeled called early. A lensing delay histogram labeled clocks. A UDG histogram labeled environment. Under each they write one rule: no moving goalposts. When a favorite theory misses, they don't switch teams, they circle the miss and keep the plot. You can adopt the same habit with headlines. When you see direct proof, ask, consistent with what, under which assumptions? When you see theory shattered, ask, photometric or spectroscopic, pre-registered or retrofitted. Curiosity beats belonging. Why it matters. Institutions nudge neat stories forward. That's not evil, it's gravity of a different kind, budgets, deadlines, attention. Your role is to reward the opposite pull, clean risk. Share the plots that publish nulls. Signal boost the protocols that freeze priors. Praise the paper that writes fail on page 1. That's how fields change without burning down what works. Wonder survives this. If gravity is emergent, you live in a universe where geometry is information behaving at scale. If dark matter is a superfluid with 2 faces, You live in a universe that changes phase like water. Solid rules here, liquid rules there. If a hybrid wins, you live with a patchwork that earned its stitches in public. None of that steals awe. It makes awe accountable. Micro story. A teacher opens class with 3 images, a flat rotation curve, a bullet-style overlay, and a JWST deep field. She asks, "What would change your mind?" Students write numbers, not feelings. A delay by this percent, a dispersion bump at that radius, a stream gap rate in this band. 2 months later, a lens delay lands outside the posted tolerance. They don't cheer or boo, they update the ledger. Direct address, keep a short list. UDG external field sample, watch the posted histograms. 3 named strong lenses with long monitoring baselines. Compare delays to frozen kernels. 2 open clusters straddling the threshold. Look for bumps with locked membership cuts. 1 stream with a pre-registered gap threshold. Count kicks honestly. If those nails crack the bandage, gravity's hidden rule gets louder. If they don't, trust in the default grows for the right reasons. Either way, you've tied your belief to receipts, not rhetoric. One last habit. When a result surprises you, don't rush to explain it away. Sit with the discomfort for a day. Then ask for the protocol. If there isn't one, you already have your answer. Resolution and meaning. The universe didn't change. Our story did, and the next chapter is being written in public with dates on the margins. If you want to see which nails bend the bandage, UDGs in clusters, lens clocks, Gaia clusters, watch the next piece. Subscribe if you want predictions before plots, misses as headlines, and science that earns trust where everyone can see it. One question to leave open. What if the missing mass was never missing, and gravity's quiet rule is about to speak?